Hello everyone, my name is Yiming Zhao. My presentation is about the paper Improved Algorithms for Distance Selection and Related Problems. This is a joint work with Dr. Haitao Wang. Okay, let's start. The distance selection is a very fundamental problem in computational geometry. We are given a set P of n points in the plane and another integer k, which is in this range, and the target is to find out the k smallest interpoint distance lambda star. Okay, here's an example. We have 4 points, and all of the 4 points can generate 6 interpoint distances, and we use epsilon of p to denote the set of all pairwise distances. Okay, and the size of epsilon p will be n squared. In this example, we have 6 interpoint distances. We can enumerate them on an axis from left to right as those little blue solid triangles, and the target is to find out the k smallest one. And the decision version of this problem is try to decide whether lambda is less than or equal to lambda star for any given value lambda. One straightforward solution for the distance selection problem will take n squared time. So we can just compute all n squared interpoint distances explicitly, and then we invoke the linear time selection algorithm on those n squared critical values to report the k smallest one. And many scholars had proposed lots of subquadratic time solutions, and those solutions can be categorized into two types. The first type is the deterministic solutions. We can see that from 1985 to the previously best solution, which was proposed by Katz and Sharir in 1997, the time complexity was improved from n to the power of 9 over 5 to the n to the power of 4 over 3, of course with some logarithmic factors. And the second type is randomized algorithms. We can see the best randomized algorithm so far was proposed by Chen and Zhao in 2022, which takes n to the power of 4 over 3 expected time. And there are also some other solutions whose time complexities are sensitive to input parameter k, like Chen and Wang solutions. Now we propose a new deterministic algorithm for the distance selection problem, which runs in n to the power of 4 over 3 times log n time. This reduces one logarithmic factor comparing to Katz and Sharir's result in 1997. Although the state-of-the-art randomized algorithm runs in n to the power of 4 over 3 expected time, which in 2022, our solution is the first progress on the deterministic track in recent 25 years. Let's first review Katz and Sharir's algorithm before introducing our new solution. Okay, their algorithm proceeds in stages. They will maintain an interval ij which always contains the desired value lambda star. This interval is initialized to the range from 0 to the infinity in the beginning, okay, like this. And they will try to compute a new interval ij from ij minus 1 in the j stage. They also guarantee that the number of interpoint distances among all the points of P in the newly computed interval ij is a constant fraction of the number of interpoint distances within the range ij minus 1. Okay, this is a very important property, and by doing this, they can shrink the interval ij iteratively, and some critical values will be discarded. And after log n stages, well, ij will only contain a sufficiently small number of critical values from which we can easily compute the desired value lambda star. The algorithm relies on a technique called batched range searching. We refer to it as BRS. The target of BRS is try to find out all the pairs of points in P whose interpoint distances are within a specific range, for example, ij minus 1. Let's consider this red point is at P. Basically, all the points whose distances to this red point are within range ij minus 1 must lie in this ring region, right? For example, these 3 blue points. Now let's consider another red point at P. We can see that those 3 blue points are also in the ring region corresponding to this red point. So actually we can pack them up and build a complete bipartite graph with respect to these 2 red points and 3 blue points like this. And this can be used to record this information. As a result of this idea, we can compute a collection of n to the power of 4 over 3 edge disjoint complete bipartite graphs gamma, which contains a lot of bipartite graphs like this, AT times BT. And each AT and BT is a subset of P. The total size of AT and BT is n to the power of 4 over 3 times log n, which is also the time and space complexity. One important property of gamma is that it exactly records all pairs of AB in set P whose interpoint distances are within a specific range ij minus 1. And this value will be the number of pairs of points in P whose distances are in the specific range ij minus 1. And the counting variant of BRS is used as the decision algorithm in Katz and Sharir's algorithm. Let's consider details in the J stage. The first step is to perform a BRS on set P with interval ij minus 1. This will give us information about the pairs of points whose interpoint distances are within ij minus 1. We can see that there can be n-squared critical values within ij minus 1 in the worst case. So we will construct LPS expander graphs on collection gamma to only gather n to the power of 4 over 3 times log n critical values like this. We can see that some red hollow triangle will be ignored. Okay, only n to the power of 4 over 3 times log n critical values will be gathered. And we will run binary search on those gathered critical values with the help of the decision algorithm. By using the LPS expander technique, we can still guarantee that the number of critical values in the maintained interval is always a constant fraction. Okay, it's always a constant fraction of the number of critical values in the last maintained interval. Okay. And then by doing the binary search, we can shrink the interval to ij, to a new maintained interval. And the call-like technique is used to ensure the number of calls to the decision algorithm is always a constant in each stage. So by doing this, each stage will take n to the power of 4 times log n time, and in log n stages, we can reach the final stage and compute the desired value lambda star easily. So the total time complexity will be n to the power of 4 times log square n time in Katz and Sharir's algorithm. Now let's talk about our new technique called partial background searching, or partial BRS. Recall this figure. We will build a complete bipartite graph for those 2 red points and 3 blue points to record the distance information. Now let's consider another 2 green points like this. We can see that for the lower green point, the distance between it and those 2 red points are within range ij minus 1. But this is not for the upper green point. In the traditional BRS, we may do nothing for them. But in the partial BRS, okay, we may pick them up and build another kind of complete bipartite graph for those 2 red points and those 2 green points. As a result, we will have 2 collections of edge disjoint complete bipartite graphs, gamma and pi. Each of them contains some bipartite graphs like AT times BT or AS prime times BS prime. Each of them is a subset of set P. And then we have 2 important properties. The first one is that each pair AB recorded in collection gamma will have an interpoint distance that within range ij minus 1. And for any pair of points in P whose interpoint distance that is in range ij minus 1, this pair must be recorded in either collection gamma or collection pi. So this implies that some pairs of pi, okay, their distances are in range ij minus 1, and some pairs are not. So we call pairs in pi as uncertain pairs. We can see that the traditional BRS can be viewed as a special case of our partial BRS when pi is an empty set. And another thing is that the sizes of gamma and pi can be controlled by a preset parameter, and the time complexity of our partial BRS will increase, okay, when the number of pairs recorded in collection gamma increases. And the partial BRS, our partial BRS can be implemented by the hierarchical cuttings. Now let's talk about our new distance selection algorithm. Okay, one important keystone of our solution is a new decision algorithm which was proposed by Wang in 2022 that runs in n to the power of 4 over 3 time, and our solution also proceeds in stages, maintains an interval ij that always contains the desired value lambda star. In the J stage, the first step is to perform a partial BRS on set P with interval ij minus 1 in n to the power of 4 over 3 time, where we have 2 collections, gamma and pi. Each collection has this number of graphs. One important thing is that the total number of uncertain pairs recorded in collection pi is n to the power of 4 over 3 times log squared log n. This is relatively small comparing to the number of pairs recorded in collection gamma. You can see this figure. All red solid triangles are critical values induced from collection gamma, and those green solid triangles are values recorded in collection pi. Next, depending on the number of pairs recorded in gamma, we have two cases. If this value is larger than n to the power of 4 or 3 times log n, we will proceed to shrink the interval ij minus 1. And we will construct LPS expander graphs on collection gamma only and gather n to the power of 4 over 3 critical values. So some red triangles will be ignored. Like those red hollow triangles will be ignored, and we only focus on the red solid triangles, which are gathered critical values. Then we will perform a binary search on those gathered critical values by using the new deterministic algorithm. And this will generate a new interval ij, like this. Those blue critical values, the blue values will be discarded. Although some critical values from collection gamma are ignored, and although we don't care about the uncertain pairs recorded in collection pi, we can still guarantee that the number of critical values in the maintained interval ij is always a constant fraction number of critical values within the range ij minus 1. And the call-like technique is also used to ensure the number of calls to the deterministic algorithm is constant in each stage. If the number of pairs recorded in collection gamma is less than this threshold value, well, then this will be the last stage, and we compute all the interpoint distances from all pairs of collection gamma and pi explicitly, no matter they are uncertain or certain. The total number of critical values at this time will be n to the power of 4 times log n, and then the desired answer can be found from those critical values very easily by just using the new deterministic algorithm and binary search. In summary, so each stage of our algorithm before the last stage will take n to the power of 4 over 3 time, and the last stage will take n to the power of 4 over 3 times log n time. And we need log n stages to reach the last stage, so the final time complexity of our algorithm will be n to the power of 4 over 3 times log n. We have combined our techniques with some other tools and obtained two algorithmic frameworks, which are very helpful for solving some optimization problem whose answers are certain interpoint distances for a set of points in the plan. As long as the TD time deterministic algorithm is available, the final solution will run in this amount of time. And the basic idea is just replacing the deterministic algorithm in our new distance selection algorithm by the TD time deterministic algorithm. Following the workflow of performing the partial BRS, gathering critical values by using the LPS techniques, doing binary search with the call-like technique, finally, we are able to find out the desired value. And some applications of our frameworks include the discrete Fréchet distance with shortcuts in both two-sided and one-sided variants, and the reverse shortest path problem for the unit graphs. We can see that our frameworks bring some improvements on these problems comparing with the previously best solutions. We believe that our techniques can find many more applications in the future. Thank you.